Okay, this is the homework for section 3.5 on exponential growth and decay. So let's jump right in. And number 7 gives us an equation of y equals 2e to the x over 4. So this is really the first time we've dealt with stretch and compress. And so there's a couple ways you can deal with that. You can either use your rules for stretches and compresses, or you can, if you're trying to identify a graph, you can pick a few values. So I could pick x equals 4, and 4 over 4 is 1, so 2 times e to the 1 is probably a pretty big number. Like if e to the 1 is 2.7, so 2 times that is about 5.4. So that maybe wasn't the best number to pick, but at least, now I'm looking on my graph, and at 1, 2, 3, 4, I'm already expecting to be up here at 5, and I know that's an exponential. So why don't I pick 0 and see what happens? So 2 times e to the 0 is just equal to 2. So that's going to tell me my y-intercept, and yeah, so basically I'm looking for an exponential that crosses at 2, 0, and goes up kind of a little bit slower. So that's going to be choice C. In number 11, I'm actually got a logarithmic equation, or a natural log. So the natural log of x plus 1, I'm expecting to see my natural log function, which is going to look exactly like the logarithm function. So here's the parent, and then plus 1 is going to be left 1. So I'm expecting to see something with a vertical asymptote at -1 and crossing over at the origin. So that is going to be choice D. Number 13 is an interest formula problem. So let me go ahead and copy the table a little bit, because I've got to do 13 and 15 on this one. So my initial investment is P, my rate is R, the time to double, and the amount after 10 years. And so that's actually giving me a little bit more information, because that's telling me t equals 10. Okay, so in number 13, we're given the information. We've got a $10,000 initial investment. We've got a 3.5% interest rate, which I'm going to go ahead and, let's see, I moved that over too many places. 0.035. I want to know how long is it going to double and how much is there after 10 years. And interest is compounded continuously. So I'm going to start with A equals PERT on both of these. And then my final amount for doubling would be 20,000, and then I would have my 10,000 right here. So remember, we did some problems like this where we went ahead and did the 20,000 divided by the 10,000. So this 2 right here signifies doubling. So e to the r 0.035 t. So now t is my only variable there, and I would want to use my loop trick. So the natural log of e of 2 equals 0.035 t. So the natural log of 2 is going to be 0.693 equals 0.035 t. So I just need to divide that out to find my answer. So I can do that, 0.035, and that gives me 19.8. T equals 19.8 years to double at 3.5% interest. Then if I'm looking for the amount after 10 years, I'm simply going to A is my missing variable, and I'm going to substitute 10,000 times e to the 0.035 times 10. So plugging all of that in, 0.035 times 10, just move it over one place. So e to the 0.35 is 1.419, and then that times 10,000 gives me 14,190.68 cents. Okay, and so that was number 13. Now let me look at number 15. So I'm just going to extend my columns to give myself a workspace for number 15. And the information given in that one, I'm given $7,500, and I don't know my interest rate, but I know that that thing takes 21 years to double. And that is the only information that I have. So I'm going to work backwards in this problem. See, the last time I was able to solve for the number of years. This time I'm given the number of years. And I really need to find my rate so that I can use that to solve the last problem. So in my time to double problem, I know my final amount will be double of the 7,500 and then my initial. So I'm going to show you why that works to put a 2 right there. So I would have 15,000 equals 7,500 times e to the r, and then t is 21 this time. So you can see I still only have one variable in the equation, which is why I'm able to solve it. So divide both sides by 7,500 and I get 2 equals e to the 21r. Use my loop trick, and I have natural log base e of 2 equals 21r. So divide both sides by 21 and I'll get r equals, so I'm going to do the natural log of 2 divided by 21, and that's 0.033. So 0.033 or 3.3%. So I can put that right there, and then now my final amount after 10 years, starting with 7,500, going with e times 0.033 times 10. And so now I'm just plugging that in. E to the 0.33 is 1.390 times 7,500, and we get 10,432 and 26 cents. Okay, number 21, let me get a new sheet of paper here. Number 21, I've got another table to complete, so let me do some copying here. I've got different interest rates. And even though these problems take time, I like them because it sort of goes back to the problem that we did on saving for retirement, and it really shows how different percentage interest rates will change your investment. So I want to know how many years t will it take for p dollars to triple. So I'm going to base this on PERT. But remember, when we're tripling, we basically have any amount that we start with and any amount at the end that's tripled. So we're going to be replacing the A and the P here. I know that whatever my final amount divided by my initial amount is going to be 3. So 3 equals E, and then I'm just going to plug in my different values, 0.02 times T. And so I could set up my logarithmic equation. The natural log base e of 3 equals 0.02 t. So I'm going to take my natural log of 3. No, wait, that was e. Natural log of 3, 1.0986. Divide by 0.02, and I get 54.9 years. So I'm going to set up the equation one more time, and then we're going to see that there's a pattern here. So 3 equals e to the 0.04 t. Natural log of 3 equals 0.04 t. So now I'm taking the natural log of 3 divided by 0.04 and getting 27.47. So it kind of looks like half of the number, but let me keep going. Natural log of 3 divided by 0.06, and that's 18.3. And so it's not going by half. Of course, it's a logarithmic function, so it's going to be following some curve. Natural log of 3 divided by 0.08. And that's 13.73 years. Natural log of 3 divided by 0.1. 10.99 years, and natural log of 3 divided by 0.12, that's 9.155. So obviously the higher the interest rate, the shorter amount of time you have to wait for your money to grow to be 3 times as big. Alright, number 27 through 33 odd. Let's see what we're getting into. We've got radioactive decay and half-life. So we've got, let me just make my table. Well, yeah, I'll make a table even though I only have one problem to do. I've got different isotopes that have different half-lives. And so we're going to look back at the half-life formula, which is really just an exponential decay. The initial quantity and the amount after 1,000 years. So in number 27, my isotope is carbon-14, and its half-life is 5,700, and we're given an initial quantity of 3 grams. So I need to go back and find my carbon dating. So okay, so to solve this problem, I'm using my decay formula, and I've got a final amount and an initial amount and then a ratio that's given. The problem is this 5,700 year half-life in the formula that's given in the example in the book. We've got carbon dating with a half-life of 5,700 years, but then the formula goes like this. We've got our initial amount, and I'm just going to call it P for now, is e to the negative t over 8,223. Apparently, because of the half-life of 5,700 years and something to do with the carbon ratio of carbon-12, we end up with this constant of 8,223. So in this problem, we're plugging in, we're looking for the final amount. The initial amount is 3. We've got E, and then the time that we're given is 1,000 years, so over 8,223 is our constant. And so after we plug all of that in, it's just a calculator problem. We end up with 2.66 years. And is that our last? No. So, all right. So moving on, let's look at number 29. And hopefully that is a decay problem. Okay, so we're given a graph in number 29, and I'm going to just sketch it here. We've got a point 0, 1, and we've got the point 3, 10. And it's a growth function. And we're looking for the exponential model y equals a e to the bx that would give us this growth model. So basically I need to find out what a and b are. So I'm going to substitute both of my points. I'm going to start with 1 equals a times e to the b times 0. So right away I'm going to get e to the 0, which is equal to 1, so 1 equals a. Then I'm going to substitute my other point. 10 equals, so a is 3, no, a is 1, e to the b times 3, because that's what x is. So let me rewrite that. 10 equals e to the 3b. Now let me loop trick it. Natural log base e of 10 equals 3b. So the natural log of 10 is 2.3. Divide by 3, and I get 0.77 for b. So my equation for that should be y equals 1 times e to the 0.77x. And in number 31, here I've just got a table of values, 0 and 5, 4, and 1. So I'm going to substitute those in the same way when x is 0. So e to the 0, when x is 0, y equals 4. So that's going to be a 4 over there. 4 equals a times e to the b times 0. E to the 0 is 1, so a is 4. And then in my other ordered pair, I'm going to substitute a 1 for y. 1 equals 4 times e to the b times 5. I'm going to say 5b. Okay, so dividing by 4 on both sides, and I get e to the 5b equals a 4th. And now I'm going to loop trick it. The natural log base e of a 4th equals 5b. So the natural log of a 4th is a number divided by 5, and that gives me b equals 0.277. So my final equation would be y equals 4e to the, that was negative 0.277, negative 0.277x. And last one, number 33, it looks like we're looking at some population change here. So let's get a new sheet of paper. And number 33, we've got population of Pittsburgh from 2000 to 208. Here's my formula, 333.68 e to the negative 0.0099 t. So it looks like, where t is the year and 2000 is the first year, but it's kind of looking like we've got the population is going downward. So, oh, and I just answered part A. So that's decreasing because it's got a negative there. So in part B, what was the population 2005 and 2008? So if t equals 0 is 2000, then t equals 5 is 2005, t equals 8 is 2008. So let's plug it in. We've got 333.68 times e to the negative 0.0099 times 5. So 0.0099 negative times 5 equals, I'm going to do my e times 333.68. So 317.56 equals, what is it, P. Okay, so that's their population in thousands, so it would be 31,756 in 2005, and then I'm expecting for t equals 8 for it to go down. So I am going to 0.0099 negative times 8 equals, take that to the e power times 333.68, 30827. And now in 2008 the population is 30,827. That was number 33, so that is the last one in this section. Thanks for watching.